I'm going to go over some of the Chapter 3 discussion questions. So what I mean by that is I don't put up the discussion just to make you have busy work and something extra to do. I actually do it because I'm looking for some feedback. Since it's online for most of the students, I don't get a lot of feedback on what people are having trouble with, since I only have a few people actually show up during class. So I try to read those and see where people are having trouble. I try to give other students a chance to answer before I butt in though, so that's kind of why I'm butting in at the end here once the discussion is closed. But I do want to address some of the questions that weren't answered in the discussion. Now this is covering both sections, so it's covering this section and then I have a second section as well. So I looked at all of those discussion questions because usually if one person has the question, someone else does. So I'm going to start by addressing some of those before I start the Chapter 4 problems. And then I'll also talk about the information literacy assignment. Some of you may have seen me post a folder on that under course content in the Blackboard shell. So I'll talk about that and discuss exactly what that is. So starting with the discussion. So this is Chapter 3, so this is back thinking Newton. Okay, remember Chapter 3 was all about Newton, it was about forces. One of the questions I had, and I'm assuming that it has to do with the quiz itself, was someone said, I thought that Newton's law was the law of gravity, not inertia. Okay, so I wanted to address this because I think there's some confusion. Newton has several laws. He has, first off, the 3 laws of motion. And so if I'm asking which of Newton's 3 laws of motion, I'm looking for one of these 3. I'm looking for either, is it the law of inertia, which is the first one, and that is an object at rest tends to stay at rest unless acted upon by an outside force. An object in motion tends to stay in motion unless acted upon by an outside force. Okay, so this is one of Newton's laws, but it's under the heading of the 3 laws of motion. Okay, so if I'm asking about the 3 laws of motion, I'm asking either about the law of inertia, or I'm asking about the second law of motion, which gave us the force equation, mass times acceleration. Newton's 3rd law of motion, that one is for every action, there's an equal and opposite reaction. Okay, so this is the one, a lot of people remember this one where I have an image of punching someone in the face. Right? The harder you punch them, the more force is exerted back on your hand. Okay? So for every action, equal and opposite. I'm not going to write the whole thing so you can see it on the PowerPoints, but equal and opposite reaction. So he has these 3 laws of motion, but then he also has the law of gravitational force. This law is not under the heading of the 3 laws of motion. Okay, this is a separate law. And this law of gravitational force, that's that F of G equation that we've used, where every object on Earth exerts a force on everything around it, and every object around it exerts a force back on that object. Okay, so these are those tiny, minute forces that we calculated using that gravitational constant, that G, that 6.67 times 10 to the negative 11th value. And then m1, m2 over r squared. Okay, so these are 2 separate things, but yes, Newton came up with them all, so you need to be able to distinguish. If I'm asking about the 3 laws of motion, I'm asking about one of these 3. I think I gave the law of gravity as one of the multiple choice, and that's why it confused people. Because yes, Newton came up with the law of gravity, but the law of gravity is not one of the 3 laws of motion. And I'm making a lot of assumptions here because the question was slightly unclear, but this is where I'm thinking that confusion came from, or that question came from. When they said they thought that the law of gravity was Newton's law, not the law of inertia. Well, both are. Okay. So another question I had, maybe someone in class can shed light on it, was someone said they were having trouble converting acceleration and force. Okay, so you can't convert between acceleration and force. What I mean by that, acceleration, for instance, the units on it are meters per second squared. For force, the units on it are newtons, but what newtons are, okay, so let's look at the equation that we get from Newton's second law of motion, force equals mass times acceleration. Mass is kilograms, acceleration is meters per second squared. So newtons is the same units as if we wrote kilograms times meters per second squared. So we can never convert from force into acceleration. So I'm thinking that this question was maybe they had trouble solving for acceleration using this problem, perhaps, using this equation. So if you're trying to solve for acceleration using the force equation, trying to rearrange for it, just to show that again, if you need A by itself, you're trying to get acceleration by itself, you divide both sides by m to get rid of it. So that'll cancel out mass, and then acceleration will be force over mass.
Don't you usually like convert in units anyways before you solve an equation?
Yes, so
Like you convert to kilograms and meters if you had to.
right, so if you're using this equation, your mass needs to be in kilograms. If it is not, you would have to convert the grams into kilograms first. Your acceleration also needs to be in meters per second squared, but I never give it to you in anything other than meters per second squared. So you never have to convert acceleration. Okay, the mass, I do sometimes give it to you in grams, then you would have to move the decimal 3 times to convert it to kilograms. And some of the problems today, I'll show you that because I have several examples that are in grams where we have to convert.
I think there were
What was that?
questions like that on chapter 3.
There were questions like that
Where you had to
go from
convert to
kilogram-
kilograms first before solving.
Yes.
No
Yep.
matter what. That might have
So that might be where this was coming
Yeah.
from? Okay. So yeah, if you use this equation, the mass needs to be in kilograms. If it's not, you have that KHD space DCM. So for instance, let me erase this. If I gave you 25 grams and you need to get that in kilograms in order to use this equation, in order to come up with force or acceleration, since it has a letter in common, this is way back in chapter 1, right? It has a letter in common, GG, that means it's metric to metric. And then you can use this scale. King Henry died drinking chocolate milk. And the letter in common is what goes in that empty space, the G. So to convert, we're starting at the G and we're going to the K. So we move it 1, 2, 3 times to the left. Start at the end of the number since there is no decimal. And then 1, 2, 3 times. What's going to go in that empty space? Excuse me if I'm tickling my throat. It's going to be a 0. So that would be 0.025 kilograms. So this would be what you would plug in as your mass in kilograms, not in grams. So maybe that's what the question was asking. But I encourage you, virtual people and people in class, keep asking questions on the discussion. I'm going to try to address them for every chapter, or email them to me and I'll address them in class. If you don't come to class, you'll at least be able to hear the answer. One person has the question, usually someone else does as well. Last question I wanted to answer was about mass. So someone asked if distance, does mass change depending on distance? No. Okay, so mass is the material that an object is made up of. So this marker has a certain mass depending upon how much material it's made up of. If I put this in a different place, it's still going to be made up of the same amount of material. What changes is the weight. Okay, so mass does not change. No matter where the object is going, even if the object goes to the moon, or to Mars, or to Jupiter, Okay, mass does not change unless a piece of that object literally falls off or is broken off. The mass is going to stay the same. What changes is weight. And the reason that weight changes is because weight is a force. That's that F of W. And it's dependent upon the mass, which does not change, and the gravity. Okay, so if the gravity is changing, the weight will change. So if you go to the moon, yes, your weight will be different. Your mass won't be. You're still the same person, made of the same material. If you go to Jupiter, yes, different gravity there too. Okay? If you go to the sun, not recommended obviously, probably burn up, but gravity would be changing there as well. So it's the gravity that's changing, not the mass, that's making your weight change. So I think I addressed that question. All right. Do people in class have any questions about force, chapter 3 at all? Okay. I've just seen a lot of comments about the equations being confusing. So for people who are having trouble with confusing equations, if they could tell me what equation, I could work an extra problem out using that, and maybe that would help clear up the equation itself. But without more information, it's hard for me to address. Just, this was confusing. So be as specific as you can in those discussions or in any questions you email me so that I can address them more specifically. Because I want everybody to understand. But I can't help if I don't know there's a problem. So with that, we're going to look at the information literacy paper, and then we'll start the chapter 4 stuff. So there is a folder under course content on Blackboard that says information literacy, either paper or assignment. I don't know which word I use. But this is not due until November 18th. But I want to get it out there now because in case you have a week where you don't have a lot of homework, you can go ahead and knock it out. Okay, it's not a huge paper. It's 500 words, which usually ends up being 2.5 to 3 pages. Okay, so it's a pretty short paper. This is a science class. I don't expect you to be writing me a 10-page research paper. Okay, I want you to more focus on the equations and rearranging them and the units and solving them. But I do want people who have a hard time with the mathematical part or have a hard time or test anxiety to get a chance to get some points doing something else. So this is worth 10% of your grade, same amount as a test. Okay? So if you do well on it, I mean, it's really going to affect your grade positively. So what it is, a research paper based on either chemistry, physics, or astronomy. Okay? So not biology, not A&P, because there's already classes here for those 2 subjects. You can take those classes if you want to write a paper on that. We don't have astronomy classes, so you can write on that. Physics, that's what we do in here. Chemistry, we're going to be doing that towards the end of the semester. So any of those topics. If it's not on the list, so I have a list of suggested topics, you do not have to use one of these. I just typed up a few just because I know sometimes people are like, I have no idea what to write about. So these are to spark your imagination. Okay, you can pick one of them. If you don't pick one of them, just email me what you do want to do. Just to make sure that it's falling in the realm of where I want the papers to be, okay? So once you pick your topic, like I said, 500 words, you need at least 3 sources. So you need a reference page. You can pick APA or MLA format, whatever works best with your major. Because I know depending upon the person's major, different instructors want different formats. I don't care. Whichever one you pick, though, be consistent throughout the paper with that format. Okay. The 3 sources, you need one from print, so it doesn't have to be, you don't have to go to the library and physically take out a book. It can be an e-book, but I want it to have been a book that had been printed. You can even use, because some of these topics, you can use the book for the class. That's an e-book. They have information on, for instance, one of the topics is about centripetal acceleration and centripetal force. You could use your book as a reference to write that paper, because it has a lot of information about that. So one book or ebook, you need one electronic source. Wikipedia you can use for information, but I don't want that as your only electronic source because Wikipedia can be edited by anyone. And yes, most of the time it's right, it's correct, but not always. So it's not a 100% reliable source. So electronic being a reputable website that you find. You also need one periodical. Okay, so for the periodical, that's a scholarly journal. You can actually access a lot of journals through the library and online. You don't have to go into the library. If you have your student ID, they have lots of different journals. They have American Chemical Society, they have the JACS journal. They have a ton of different journals that you can use. So find one of those as well. So it's due on a Wednesday, and I know that's weird, but the reason I didn't want it due on a Sunday like most of our stuff is because it's the Sunday before Thanksgiving. Everyone's gonna forget, okay? Because you're gonna get out of school on that Thursday or Friday, and you're gonna be like, oh, no school for a week. So I want you to get this in Wednesday before you turn into vacation mode, all right? And it can be turned in any time from now until that Wednesday, November 18th. So you can get it done now and forget about it. I don't accept late turn-ins on this because I'm giving you such advance notice. So please, please, please look at it, work on it when you have time in this next, what, you have almost 2 months, month and a half to work on it. When you submit it, you're going to submit it electronically, so I already have a link up. You can attach it as a Word document or a PDF. So it's very similar to how you turn in your labs, same type of link. Don't plagiarize, obviously. For the guidelines, it says New Times Roman 12-point size. If you pick a different font and the size is a little bit different, that's fine, because I'm looking at word count. So if you don't have the 500 words, you can make it size 18 and make it look like it's 5 or 6 pages, but I'm still going to be counting the words. So it needs to be 500 words is the main thing. Double space is just so that I can make comments on it a little bit easier, because I can actually write on it with a tool in Blackboard so you can see where you got points off. So, suggested topics I'm not going to read through. You can read through those on your own. I do want to give you a rubric for it, just so you can see how I'm grading it, because I always help you kind of guide yourself a little bit better. So for instance, the format, MLA or APA. So if you decide, I'm not going to do a format, I'm just going to write it how I feel. Well, you could lose 15 points. Okay, so pick a format and stick with it. If your format is appropriate, citations are good, you'll get all 15. If you have correct formatting mostly, but some mistakes, 9 to 12. So you can kind of see how this works out. No formatting at all, you'll get to 0. All right, for the references, I just told you you needed 3. You get 5 points for each one. And you need 1 from each category. So if you give me 3, but you only have 2 from each category, you're probably only going to get 10 out of 15. Okay, so you could give me 10 and still only have 2 from 2 categories instead of all 3 categories. So make sure you're getting 1 from each category. The content is worth half the paper, 50 points. So I'm going to be just looking that your paper is making sense, that you're not making grammatical mistakes, that it's flowing nicely, all of those things, that you're explaining the topic that you're proposing. And then word count's worth 20 points. So what that means is please don't turn in half a paper. Like the words matter. I want you to write at least 500. It's not a lot of words, so get them all in. Questions on this?
Yeah,
All of
do
this.
we actually need to quote our sources, or can we just paraphrase it and put this in?
Either. So if you quote, I only want, that's a good question. If you do quotes, I just want 1 sentence or less. Okay, because I don't want your paper to be paragraphs of quotes and that's it. So paraphrasing is a good alternative. If you have a huge quote, instead of quoting it, just paraphrase it and then cite right after that paragraph. Good question. Anything else? All of this is on Blackboard, so if you lose it or people virtually, you can find these same handouts in that folder, that info folder. All right, so I'm going to put that away. Now we can get to the meat of what we're supposed to talk about today. So we're starting chapter 4. This is the last chapter before the exam. So today we're going to talk about part 1, which is momentum, impulse, and collisions. On Monday, I'm going to talk about part 2, which is energy and power. So today, what we talk about is going to be in your Chapter 4 homework quiz part 1. So all of this information will be due Sunday in that quiz. Okay, same types of problems. I just posted right before I came to class some practice problems because I saw some people like to do the practice problems before the quiz, so those are posted, and I'll get an answer key posted later today if you prefer to do the practice problems before taking the quiz. But you do get 2 attempts on the quiz. I've seen a lot of people just do 1. Do both. I give you feedback for incorrect answers for most of them that tries to hint you or put you in the right direction in case you got it wrong. So try to do both attempts. Discussion, I'm seeing one of my sections is doing great at discussion. The other section, it's half the people are doing it, half the people aren't. Those are worth points. Keep doing the discussions. This is where I get my feedback, where I know what I should be teaching, what I should focus on, where I should do more examples, all of that. Okay, something, or maybe a concept I need to explain better or in more depth or differently because I just didn't explain it in a way that some students understand. Right?
For discussion, is it okay to put like vague hints towards the homework, or should I?
No, that's fine. I mean, the homework is, I want everyone to get 100% on the homework. Don't give the answer, but say, use this equation. You know, I mean, that's what I do for the feedback. I say, well, I used this equation, rearranged to solve for this variable, made sure that my units were in. Go ahead, yeah.
Yeah, because one of like the trick questions are on the first one.
Yeah, and then you could go, I got this wrong because I forgot to, what did you forget to do? In it, for instance. Convert
You were
from,
using newtons, but then convert the grams to the kilograms.
you forgot to convert the grams to the kilograms. Yes, by all means say, hey, on this one, don't forget to, that's fine. As long as you're not giving the answer. I don't want people to go up and go, number 1 was, you know. But if you're saying, hey, this one was tricky for me because I forgot to do this part, they still have to know how to do the conversion. You're just telling them, don't forget that part. That's fine. Yeah, I would love that. That's what it's for. It's for the students to communicate to each other. If you were sitting next to a friend in class, you would have told them the same thing. Pretend like you're sitting next to a friend in class. That's what it's for. Yeah, so that would be good. Any of the questions are fine. I just don't want answers, but hints are greatly appreciated. Hopefully for the other students as well. Maybe it'll encourage the students who aren't doing discussion to go look because they might be getting hints for the homework on there. All right, so we're going to start this packet that I just handed out to people here. This is the questions on the PowerPoint. So we're just going to work through these, see if we can get through them all. And then next week, like I said, I'm going to be doing the second half of chapter 4. I want to point this out. Your next homework quiz is on Wednesday. So far, I think we've only had 1 homework quiz on Wednesday, and that was the beginning of the semester when we did chapter 1. So be aware we do have 1 due on Wednesday, okay? Homework's always due Wednesday or Sunday. Most of the time it's just Sunday, once in a while on Wednesdays. The exam, October 11th, so that's a week from this Sunday, and that's going to be on chapters 2, 3, and 4. So I'm going to finish the chapter on Monday. I'm going to be using the rest of the week next week for review so that you're ready for the exam. And I'll open up the exam early. It'll be open probably Thursday or Friday, so you'll have the whole weekend to take it. You can take it early if you're confident, or study and wait till the last minute, whatever your preference is. All right, so let's do some problems. So the first one, we're talking about momentum. So with momentum is dependent upon the object's mass and velocity. So the higher the object's momentum, the harder it is to stop that object. Okay, and it depends upon both, and I use some examples in the PowerPoints. So don't just look at mass and don't just look at velocity. I think the example I used was a supertanker. Huge mass. Supertanker was a very large boat. I don't even know how to refer to it other than a supertanker. It has a very, very large mass, so its mass was very high, but its velocity is very low. Since it's so big, it can't go very fast. So you want to make sure you're looking at both, because a supertanker, for instance, has a similar momentum to a bullet. And a bullet's the opposite, right? The mass of a bullet is small. You can hold it in your hand. You know, it's not very heavy. So a bullet, the mass is small, but it goes so fast that it's got a large momentum as well. So a lot of the problems that I ask you are going to be similar to number 1, where I'm going to give you 2 things, and I'm going to say which one has a higher momentum. Don't assume just because it's the bigger object that it has the higher. Do the calculations. Okay, so that's what we're going to do now with this football player and football. So I'm not gonna write the whole question down because these questions are available for all the virtual people as well. So I'm just gonna write the knowns and unknowns. We're gonna approach it like we do all the other problems that we've done so far in physics. So we have calculate the momentum of a 110 kilogram football player. So we have 110 kilograms. What is kilograms? What variable?
Mass.
Mass, it's M. Okay? I mean, we should get used to this by now. Every time we see grams or kilograms, it's a mass, it's M. So we have a 110 kilogram football player running at 8 meters per second. So 8 meters per second, the units tell us that this variable should be, anybody? Not a speed, but velocity, yeah. Now we're going to compare this. So this is the football player. I should write player, not football. Player. To the momentum of a hard-thrown 410-gram football with a velocity of 45 meters per second. So the football's mass was 410. And then the velocity, it specifically says that this is a velocity, but if you didn't know, you could use the units, is 45. So this is the football. Notice anything about the football that we might want to change before using any equations?
The grams.
The grams, okay? So always check your units. Up here with the football player, we have kilograms, we have meters per second. These are both acceptable units for our equations. But down here, grams, we can't have that. We need to convert to kilograms. This is a step, like you just said a moment ago, that a lot of people forget, right? So let's do that right away. Let's get it out of the way. So grams to kilograms, like we looked at a second ago, it's metric to metric because it's got that G in common. So we can use the King Henry died drinking chocolate milk. I'm going to put a G in the middle because that's the letter in common. And then we start at the G and we're going to the K. So G to K, that's 1, 2, 3 times to the left. Now this number doesn't have a decimal, so I'm going to start at the end of the number. If it has a decimal, start at the decimal. But this one doesn't. So end of the number, and we're going to move it 3 times to the left. So this becomes 0.41 kilograms. Velocity meters per second, that's good. So we have the correct units. Now it's saying calculate the momentum. That's our question mark. You gotta put that, right? Question mark. Momentum is the letter P. That one's kind of hard to remember. Honestly, I don't know why it's the letter P. I knew at one point, but I forgot. If I remember randomly while I'm doing these problems, I'll let you know why it's represented by the letter P. I can't think of it at the moment. So to solve for momentum, we only have one equation, and that is mass times velocity. So for the player up top, we're going to take the 110 times the 8. For the football down here, we're going to do the same thing, but with the 0.41 kilograms. And it's important that you put this in kilograms, because if you didn't, you're probably going to write the wrong answer. So you're going to get a much higher number for the bottom one than we'll get right now. So how many sig figs? We only need one sig fig for this one, don't we? 880, so that would round to 900. So we want one sig fig. And the units. So for units, mass is kilograms. Velocity, meters per second. So that's our units, right there. kg times m/s. This one I don't know. Can someone calculate this for me? 45 times 0.41?
18.45.
18? So you said?
0.45.
0.45. And how many sig figs do we want on this one? Just 2? 2 and 2? S. So just 18, and it stays 18 because of the 4 next to it. And the units are the same. Kilograms for mass times meters per second for velocity. So you're comparing these two. there actually is quite a large difference. So which object has more momentum, the player or the football?
The player.
The player, and that makes sense because a player is going to be harder to stop than a football, right? And the more momentum, the harder it is to stop the object. I'd much rather have a ball thrown at me than a player attacking me. So the player wins, more momentum. All right. So that's how you want to approach those type. And the important thing here was getting this to kilograms, because if you didn't, you would have thought the football had more momentum. Because 410 times 45 is going to be way more than 900. Okay, so units are important. All right, so now let's take this momentum and look at impulse. So impulse is actually the change in momentum. So they're related to each other. So whenever we have the change in something, it's always the final minus the initial. So we'll see that one of the equations for impulse reflects the change in momentum. So what I mean by that, impulse is equal to mvf minus mvi. So this is one of the equations. And we get this equation because impulse is equal to the change in momentum. And I said change is always final minus initial. So it would be the final momentum minus the initial momentum. Okay, and momentum is just mass times velocity. So we really just plugged in the momentum equation to come up with this one. So that's one of our impulse equations. The other one relates impulse to force. So this is why chapters 3 and 4 are together, is because chapter 3 is all about force, and then chapter 4 brings in momentum and impulse, relating those two. So we're going to use this information from this problem to figure out what equation is going to work best. So we have a t-ball player. They're hitting a 52.1 gram baseball. So 52.1 grams, what variable is that?
Mass.
It's a mass, grams, right? But notice, grams, what are we going to need to do?
Convert.
We're going to have to convert it. Okay, so I'm just going to put a note there so that I remember to do that later. I want it in kilograms. So they're hitting a baseball off a tee at a velocity of 37 meters per second. So it said it was a velocity, so I know that's v. The contact time, so it's telling us this is a time, so that's t, is 2.1 times 10 to the negative 2 seconds. They want us to calculate the impulse and the force. Okay, we're looking at impulse. When we look at our impulse equations, now I know we have 3 of them. This one is not really an equation you're going to use. This equation is to show you where this one came from. Okay, so this is not an active equation that you're going to actually ever plug things into. So it's really just these 2 for your options. Because the top 2 are actually the same equation. So, which one is going to work? Top one or the bottom one? The top one. Okay, so when we look at this one, so we have mass. And it's the same mass in both. If it wasn't, it would say M1 and M2. That would be 2 different masses. But it doesn't. This is the same mass. They're talking about the same object. So we only need 1 mass to solve, and we do have 1 mass once we convert that into kilograms. But notice, they have 2 different velocities. VF means final velocity. VI means initial velocity. Well, it looks like we only have 1. So that's when we want to go back and read the word problem and see if there's something we're missing. So this person hit a ball off of a tee. So that ball, what was that ball's initial velocity? It was sitting on a tee. 0. It was sitting there. It was doing nothing. It's like those 0 initial velocity equations. You got to pay attention to the words too. So its initial velocity of that ball just sitting there on the tee was 0. So that means this 37, after he hit it, that's going to be the final. So sometimes you need to adjust your variables once you find an equation. And that's the case for this one. You say, well, this one's the only one that could work, but I need to reread. All right, so before we go plugging stuff in, let's do this conversion. We're going to do this conversion so many times you won't even have to write the scale anymore. So King Henry died drinking chocolate milk. The letter in common is G. So that's going to go in my empty space. That's where I'm starting at 52 grams, and I'm going to go to kilograms. So 3 times again to the left. So let me write this number again so you can have more space so you can see. Now this time, the number does have a decimal. So I'm not going to start at the end. I'm going to start where the decimal is. And I'm going to move it 1, 2, 3 times to the left. So my new decimal's here. That's going to put a 0 in that empty space. So this is equal to 0.0521 kilograms. So that kilogram amount is what I'm going to want to plug in for my mass, not the gram amount. So now all my units are where I want them, so I'm going to plug in to solve for impulse. So I get 0.0521 times my final velocity, which we said was 37. Then I'm going to subtract that from my mass times my initial. Now notice, my initial velocity is 0. So if an object's not moving, what's its momentum? 0. If an object's not moving, it has 0 velocity, its momentum is 0. So anything times 0 is 0. So you're just really multiplying those two and subtracting 0 from it, so it's not changing. How many sig figs do we need? 2? Yes, 2 sig figs because of the final velocity. What are we getting? Anyone? 1.9? Is that what you said? Anyone else? Anyone want to double check? What are the units? Well, impulse is just change in momentum. So impulse and momentum have the same units. Okay, kilograms, because we took the mass, times meters per second, because we multiplied that by the velocity.
So for force, do we have to rearrange the equation?
Exactly. So when you get to the force one, now a lot of people are going to be tempted to go back to chapter 3 and try to find a force equation that works. This is linear force, so the only force equation we have from chapter 3 is for linear force is mass times acceleration. Now we have mass, but we don't have acceleration. Okay? We could get it going all the way back to chapter 2 and using the zero initial velocity equations, but instead of going through several more steps, look at impulse again, because we saw when we were choosing equations that we have an equation for impulse that has force in it. So instead of going back and solving for acceleration and plugging that into this equation, you might just want to rearrange here. Both ways would work. Both ways will get you the same answer. Okay? So to rearrange, we want force by itself. So we're going to divide by the time. Whatever we do to one side, we have to do to the other. So time will cancel. So my rearranged equation is impulse over time. So I can plug in my 1.9, and then my time, 2.1 times 10 to the negative 2. And if you want, you can put this in normal notation before you put it in your calculator. We learned how to do that in chapter 1. Just move the decimal twice to the left to get 0.021. So dividing that out, we should get a force in newtons.
I got 90.4.
Yes.
Or 0.5.
Okay, now I'm remembering this one. So 90, it was 90.4, right?
0.47.
Okay, so we just want 2 sig figs, so that's why I stopped at 90.
Oh, okay.
It was 90.4. You look at, that's 1, 2, look at the number next to it, it would stay 90. And notice I put a decimal after it because I said 2 sig figs, so I need a decimal so that 0 counts. All right, so units, force is always measured in newtons after Sir Isaac Newton. If you could also put kilograms times meters per second squared. These are the same. Okay, it's just they named it newtons because of all the work he did on force. All right, we're going to look at another impulse problem, but we're going to look at it in terms of collision. So let's look at collisions first and then tie collisions and impulse together. So we start with momentum, which is object's mass times its velocity, and then we brought an impulse, which is the change in the object's momentum, its final momentum minus its initial momentum, and now we're going to look at collisions. So with collisions, momentum's conserved. So what I mean by that is the momentum before the collision is going to equal the momentum after the collision. Okay? And what we're going to see, since these are perfect bubble examples, okay, is that the masses before the collision and after are going to stay the same. We're not losing parts when we collide. I know in real life sometimes a bumper falls off when you get in an accident, when you collide with an object like a car crash, but we're not looking at all of those factors. We're looking at a perfect bubble. So let's look at this first collision, which you wouldn't necessarily think is a collision by just reading it. And that is a grandma roller skating. So I had this example on the PowerPoints. I had a picture of it so you could kind of visualize it. And what we have is a grandma roller skating along at, 6 meters per second? And she has her grandson there, and he's just standing still. He's not moving. So she goes along, and she scoops him up, and they roller skate off together with him in her arms. So we have two different types of collisions. In order to solve, we need to know what type, because there's two different equations depending on the type. So before we look at our knowns and unknowns, should erase this, let's look at the types. So we have an elastic and inelastic. Two different equations for both. So elastic, objects collide, bounce away from each other. Okay? So two objects, two different masses, hit each other, and then go their separate ways. So they are two objects with two different velocities after the collision as well. So the equation for this is m1 v1 plus m2 v2. It's the same on both sides. So the reason it's the same on both sides is because before the collision, we have two separate masses with two separate velocities. Once they collide, they bounce away, and there's still two separate masses with two separate velocities. So inelastic's different because in this case, the two objects collide, but then they stick together. So before the collision, we have two separate objects with two separate masses going about their way. So we have grandma and the grandson, two separate objects, two separate velocities. But then after the collision, those objects collide, and since they stick together, we add their masses together. Because since they're stuck, they're now one object, and their masses are additive, and do the sum. And their velocity is the same after the collision. Because since they're stuck together, they have to be going the same velocity. There's only one velocity after. So what type of collision is the grandma and her grandson? Inelastic. Yeah, she goes and scoops him up. Now she's holding him in her arms. So they are one object with one velocity after. So we know that we're going to be using this equation. Now all we need to know is what's our M1, what's all our variables. Let's figure those out. So starting with grandma, they give us her mass first. What was she, 80 kilograms? And I'm going to call her M1 just because it's the first mass I encountered. All right, the next piece they give us is the grandson, 40 kilograms. That's also a mass, so I'm going to call it M2. Now, that's 6 meters per second. Here's the tricky part. Who does the 6 meters per second belong to? Does it belong to grandma, M1, or grandson? grandma. So it's m1, so that means that 6 meters per second, since it belongs to her, has to be my v1. Because those two belong together. I don't want to label it v2, that'll mess up my problem. This velocity belongs with this mass, so that's why they both have a sub 1. I'm also going to need a v2. Now the v2, that belongs to the grandson. So what is the grandson's initial velocity?
0.
0. He's not moving. He's standing there. Maybe he's scared. Maybe he doesn't know how to roller skate. So he's 0. And the question is asking for the final, right? Calculate their final. So that's v sub f. Because if we look at the equation, after the collision, they have the same velocity. So it's just one velocity they're asking us to solve for, that v sub f. So notice we're going to have to rearrange. I'm going to have to rewrite this whole thing. We're going to have to rearrange it right there. That's a v2. I'm going to stop erasing with my hands. Plus 2. Okay, so we're going to rearrange to solve for the final velocity. And what we're doing is we're taking, the reason the mass is in parentheses, is we're taking that whole thing once we've added it and multiplying it by VF. So to rearrange, we do the opposite. Instead of multiplying, we're going to divide. So to get rid of it, we can divide by m1 plus m2. That gets rid of that whole thing, and VF will then be by itself. But remember, whatever we do to one side, we have to do to the other. We're going to divide this side by m1 plus m2, making sure it's in parentheses. So cancel it out on the right side of the equation to get the final velocity by itself. And then I can plug in, just write that here. So this would be my rearranged equation. So once I have it rearranged, plug in all my variables. Let's see. We have m1, which is grandma at 80, multiplied by her velocity, which is 6. We're going to add that to the grandson's. Notice this is the grandson's momentum, right? His mass times his velocity. And since he's not moving, his momentum's 0. Right? You could write it out and calculate it. You're going to get 40 times 0, which is just 0. Saves us some work there. And then we can divide that now by the total mass of both objects, both people. So we're adding 80 plus 40 on the bottom. And you need to make sure to put that in parentheses, because otherwise by orders of operation, it's going to do the division before it does the addition. So what we should see, so with collisions, is that the velocity we get, the final, should be in between the two initial velocities. So what I mean by that, since momentum is conserved, when grandma goes to grab her grandson, she's going to slow down. Her velocity is going to go down. But if her velocity goes down, we need momentum conserved. So that means her grandson's velocity has to go up to make up for her velocity going down. Okay, so we should see something between 0 and 6. And I think we get 4, if I remember correctly. Is that right? Can we calculate it? Is it 4? And we're looking at 2 sig figs, so I'm going to put 4.0. So that's just a check to do once you've solved. So if you happen to get like 10 or something negative, which you should never get a negative velocity, but if you get something higher than these two velocities, that means maybe it was calculator error, maybe you didn't put it in correctly, or you plugged in the wrong numbers. So it's just a good check to do at the end. Any questions on that one? All right, try number 4 then. So number 4 is going to be very similar. We're going to do another collision one, and then we're going to take it, and you can see in number 5 and 6, we're going to bring impulse and force back into it. So we'll do some more problems using those impulse and force equations. So myself some room here. Looking at number 4, reading it. You got two cars colliding. They're sticking together. So what type of equation is it? Elastic or inelastic? Inelastic. Okay, so we're using that top equation. I'm trying to gain myself some more room here. It's gonna take a bit. So we have, let's do our knowns and unknowns. So if the car is sticking together, we just said it's inelastic. So at least we know what equation we're using. Now we just need to figure out all our variables. So we have the first car going 15 meters per second. And that is a mass or a velocity? Velocity. So I'm going to call it V1 just because it's the first velocity I ran into. So the first car, and because it's the first car, it's going 15 meters per second, has a mass of 1,750 kilograms. So 1,750 kilograms, that's the mass, but it's M1 because it's the mass of the first car, and that first car has a velocity of 15. So those two go together. That's how we can figure out that car's momentum. The second car was stopped. So what does was stopped mean? What does that tell us? So if you're stopped, what's your velocity? 0. So the second car's velocity is 0, so V sub 2 would be 0. The second car has a mass of 1650, so our M2 is 1650. And we're calculating the velocity of the cars after impact, so the VF. So very similar to the last problem. Okay, we're using the same equation, we're rearranging it to solve for the final velocity. Since we already showed how to rearrange it, I'm going to show the rearranged version instead of doing it again. So that it's all ready for us to plug in. So when we're looking to calculate our final velocity, remember, since it's a collision, since momentum's conserved, the velocity should be in between these two numbers. And if you think about it, if you rear end a parked car, your car slows down. The parked car speeds up, starts moving. Okay, so we should see something in between here if they were stuck together. So, mass of the first car, where are we at? 1750? And his velocity was 15. And we add that to the momentum of the second car. So the second car, 0 velocity, so 0 momentum. But I'll show it written out just so you can see that that indeed is true. 1650 times 0 is just equal to 0. We divide that by the masses of the two cars added together, since they are now one object stuck together, moving in the same direction at the same velocity. So we should get 2 sig figs, somewhere between 15 and 0. 7.7? Our final velocity is going to be 7.7 meters per second. Questions on this one? Okay, so let's look at number 5. It's using the same information, so I haven't erased yet. It's saying if the crunch time was 0.1 seconds, what is the impulse and force on the first car? So what I'm going to do, I'm going to keep M1 and V1 up here because it's asking about car 1, and those two variables belong to car 1. I'm going to erase cars 2 information. I'm also going to add, notice they gave me another piece, they gave me time, 0.1 seconds. 0 seconds, okay. And they want to know impulse and force. And we've done this before. We already know what equations to use. Or at least we'll recognize it better once we see it, since we've done it once. So they're talking about just car one, impulse on just car one. Remember, impulse is change in momentum. So the final minus the initial. So going over here, we have the final velocity of 7.7, and that means this v sub 1, that's going to be our initial. The car was originally going 15 until it rear-ended another car. Okay? So let's plug these in and see what the car's impulse is. What is its change in momentum? So the mass of the car is 1750. The final velocity is 7.7. Subtract mass of the car, also 1750 because it's the same object. And then the initial velocity was 15. And it looks like we're going to get a negative impulse, and that's fine. It can be negative. I'm trying to remember, was it 13,000 when you rounded to 2? 12,700 or something?
Yeah.
12,007 something?
Yeah.
Yeah?
7,000.
Okay, so we need 2 sig figs. So when you round it up, it's negative 13,000 kilograms times meters per second. I'm going to do I1 because it's the impulse on car 1. Because if you'll look ahead a little bit, you'll see we're going to calculate the impulse for car 2 as well. All right. So now let's look at the force. Because it wanted us to calculate the impulse on car 1, but also the force on car 1. So remember when we did this last time, I think this was like the second problem we did today, we used this equation, rearranged to solve for force. So we divided by t on both sides to get force is equal to impulse divided by time. So we're going to take that negative 13,000 and divide it by 0.1. So we're going to get a negative force as well, and that's fine. Force is a vector quantity, so we can get a negative number. That tells us what direction. Okay, we have plenty. So we have a negative impulse, a negative force for car 1. So why are we calculating this? Well, notice number 6, we're going to do the same stuff for car 2. And what we're going to see, this is proving that momentum is conserved. It's also proving Newton's third law of motion, where we said for every action there's an equal and opposite reaction. For every force, there's an equal and opposite force. So you can bet money that when we calculate car 2, its impulse is going to be the same magnitude, so the same number, but a different sign, opposite. Same with force, same number, opposite sign. We'll see a positive 130,000 newtons because Newton's third law is true. For every action, there's an equal and opposite reaction. This applies to force as well. So let's use that. I'm going to circle this because this is going to stay the same and this is going to stay the same for car 2 because this was their final velocity, both cars, and this is the time of the accident. But let's bring in the velocity of car 2 was 0, right? And the mass of car 2 from number 4, what was that, 1650? So what number 6 is asking, using this information, calculate impulse again and force again. So same steps, different numbers. So impulse. Change in momentum, right? Different mass and different initial velocity. So we have 1650 for the mass of car 2. The final velocity is the same because remember it was an inelastic collision. They were both going the same velocity at the end. The second part, well, this car was initially stopped, so its initial momentum was 0. So if if you multiply 1650 times 7.7, what you're going to get is positive 12,000 something. But when you do 2 sig figs, like you're supposed to, it should round up to positive 13,000. Making it equal in magnitude to car 1, but opposite in direction. Because it's the opposite charge. So this is the impulse for car 2. Showing that momentum is conserved. Okay, the change in momentum for car 1 is negative, the change in momentum for car 2 is positive. They cancel each other out, making a total change of 0. So let's look at force. We said it is impulse divided by the time. So we're taking the impulse of car 2 to figure out the force of car 2. Dividing it by the crunch time. How long did that accident take place? What was the crunch time of the accident? So I2 was 13,000 divided by 0.1, and we get 130,000 newtons. So, same magnitude as the force of car 1, but opposite direction. So this part is proving Newton's third law of motion. For every action, for every force, there's an equal and opposite force. So whatever force that first car applied on the parked car, they applied the same force back. That's what that's showing. With numbers. All right. Questions so far? A lot of calculations just to prove the laws, but so we've done inelastic, we've applied impulse and force to it. Let's look at a different type of collision. That's what number 7 is going to do for us. I want to change the wording of number 7 a little because I had someone in class yesterday in a different section that pointed out I'm not an air hockey player. And number 7 talks about air hockey. And my assumption with air hockey was that if the table is balanced, the pucks aren't going to move. And they pointed out that that's not true. The pucks do move a little bit no matter what. Okay, so that doesn't work for this problem because I need the pucks to be motionless until they're being hit. So instead of imagining air hockey, we're going to imagine a pool table. Because on that one, I know that the balls are still until they're hit by another ball. Okay, so change the wording a little. Imagine playing pool instead of playing air hockey, just so it fits the parameters better. All right. So for number 7, we're playing a game of pool instead of air hockey. And we have a 50-gram ball. We're going to call it a ball instead of a puck since it's pool. They're shooting a 50-gram ball at 9 meters per second, hitting a blue ball with a mass of 45. One of the balls stops upon impact, sending the other ball ahead. So if you're playing pool, you can kind of imagine this. You hit the cue ball, it hits another ball, the cue ball stops upon impact, making the other ball move. So that's what we're looking at here. Okay, so let's make our list to kind of envision this with the variables. So what type of collision is this? We have one ball hitting another ball, stopping, and sending the other ball going. So we have a collision, one ball stopping, and the other one moving. Are they stuck together? No. So it's not inelastic, so it must be the other type, elastic. They're not bouncing, they're not both going separate ways, but they're not together. And that is not so elastic. Can't talk and write at the same time. All right, so let's look at the mass of ball 1. What was it, 50? It was grams, correct? Okay. And then, oh, I didn't do the correct suffix, so 50.0. How fast, what was the velocity of that ball? 9? 9.0. And then this ball, we hit it, it was 9.0 meters per second. It hits ball 2 with a mass of
45 grams.
What was ball 2's initial velocity? So we're looking, this is all before the collision. So we have the mass of ball 1, and it's going 9 meters per second. We have hit it, it's going 9. It's going towards ball 2. What is ball 2 doing? What is ball 2's velocity? 0, it's not moving. So we're looking at, this is why I had to change it from air hockey. It's not moving, it's sitting motionless, so 0 before the collision. It's not moving before the collision. Now after the collision, we'll put those down here. After the collision, the masses aren't changing. They're going to be the same. It's the velocities that are going to be different. So after the collision, what is ball 1 doing after? What's its velocity? Does it give a velocity? Does it say it stopped? It stopped. So ball 1's velocity, it hits ball 2, it stops. So after the collision, it's motionless. What is ball 2's velocity? Is that what we're solving for? Okay, that's the question mark, saying what's the velocity after? So lots of variables going on everywhere. So the reason I wrote a specific before and after on this one is because with elastic problems, it's the same on both sides of the equation, right? It looks exactly the same. Okay, so we need to specify that this side we're going to put in our before numbers, and on this side we'll put in our after numbers. Now the masses are staying the same on both sides because I said in a collision, you're not losing pieces as you go. So your mass, the amount of material that object's made up of, is going to stay the same. So plugging in, and notice, let me point out, these are in grams. And so your first instinct might have been, let's change it to kilograms. And yes, that is correct. However, you don't have to, you can, and you'll get the right answer. But you don't have to because we have mass on both sides of the equal sign. So if you have mass on both sides, as long as the units are the same, you're good. You can keep it in grams. Because they'll cancel out. When we get our final answer, we're going to get meters per second. We're just looking to make sure the units of the mass cancel. And as long as the units are the same for both masses, you're good. If you changed it to kilograms, that's fine. You'll get the same answer. The masses will cancel. You're still good. But to save you a step on this equation only, you can keep the masses in grams. You don't have to do that step. So, with that said, let's plug them in how they are. We get 50 for mass 1. The velocity before was 9. Ball 2, notice ball 2, 0 velocity, so his momentum, 0. I'll write it out anyway, just to show. After, we have the mass of ball 1. That's the one that stops, so now his momentum is going to be 0, right? He's 50 grams, but he's going 0, so anything times 0 is 0. But for M2V2, we have a mass of 45, and the V2 is what we're trying to figure out. So I'm going to get rid of all of this messiness and kind of make it look a little cleaner here. And the reason I plugged numbers into this one instead of rearranging first is it was going to get really messy to rearrange it. So on this one, you'll probably want to plug in the numbers because you're going to get a lot of zeros that you can take out and not worry about those variables and how to rearrange those. So I have 45V2 over here. What's 9 times 5? 45? That's 450. Is that right? Did I do that wrong? Can't be that easy. That is right? Okay. So 450, so multiplying 9 times 50 gives me this. And then I have 45 V2 over here. I don't know why I have 45. Yeah, it's 45 grams. Okay. So I want V2 by itself. So this is just like if they were variables. Okay? I'm taking 45 and I'm multiplying it by V2. I want to get rid of the 45, so I'm going to do the opposite of multiplication, which is division, and divide by 45. 45 divided by 45 is just equal to 1, right? So it cancels. But I have to make sure to also divide by 45 on that side. So I have V2 is equal to, and I need 2 sig figs, is that right? Yes. 10 meters per second. Now, I've told you on those inelastic problems, and I want to point this out because someone might see this and have a question later, that you always want a velocity between the two initials, right? So why is that one higher and correct? It's because of the mass difference. So I said momentum is conserved, right? So the mass of ball 1 is higher than the mass of ball 2. So this is a perfect frictionless surface where we're not losing anything. So in order to make up for this mass difference, the velocity of ball 2 has to be a little bit higher so the momentums are the same. So what I mean by that, if you multiply these two together, that should be the same, because this is ball 2, as if you multiplied these two together. Because the momentum needs to be conserved. So 50 times 9, we just said it gives 450. 45 times 10 gives 450. So it has to be a little higher so that momentum is conserved, so that they have the same momentum. Okay? You'll only see this happen where the velocity is a little higher in elastic collisions. In inelastic collisions, you'll always see where it has to be between the two initial. Because elastic is when they're colliding and then moving off together. So one of them lost, one of them gained speed. So it's going to be in between their two speeds. Here, they hit and went separate ways. So when this ball 2, when ball 1 hit ball 2, it stopped. So it gave all of its momentum to the second ball. So in order to give all its momentum to it, that means the second ball had to go slightly faster since it was lighter, since its mass was less. Or you could just say, hey, I calculated it right and leave it there. But I was trying to explain concept-wise why this is higher. So we didn't get to the last problem, but I did do that in another video that I've already posted up on Blackboard.